Today I'm going to talk about solving a system of linear equations. Here I've got two linear equations with two unknowns. Here's a system of three linear equations and three unknowns. An equation is linear if it can be expressed in this form right here. Well, if it's an equation with only two variables, that's the standard form of a linear equation, at least one standard form, where a and b and c are just real numbers, x and y are my variables. Geometrically speaking, that represents a line. So over here, geometrically speaking, this represents the system of two equations and two unknowns, where these two equations represent two lines that can either not intersect at a single point, or maybe intersect at infinitely many points. So with a system of linear equations and two unknowns, I can only have zero solutions, exactly one, or infinitely many. Now over here, here's a system of three linear equations, three unknowns, but a linear equation with three variables does not represent a line in three space. That's going to require some discussion of vector valued functions. Instead, one equation and three unknowns that's linear represents a plane in three space. So yet again, there could be three parallel planes. That's just an example of having no solutions. Maybe they all intersect at a single point, or maybe they intersect at a line, or maybe they intersect upon a plane. All three planes are the same. So here too, with three equations and three unknowns, as long as the system is linear, I'll either have exactly zero solutions, one, or infinitely many. So let's talk about solving such a system using a new technique, because back in ninth grade algebra, you already had the two tools in your back pocket called the substitution technique, and the other was called the, actually, I don't know what it's called. Some of you called it the elimination method, some of you called it the addition method. I don't want to talk about those techniques. I assume they're in your back pocket. I want to talk about another technique, which is what I refer to as Gauss-Jordan elimination. Or some people say, is a technique of rewriting a system as a single matrix and then row reducing that matrix. So, fancy word matrix. My formal definition of matrix is this simple. It's just a rectangular array of numbers. As far as I'm concerned, I don't really view this as a real matrix. When I say it's an augmented matrix with the adjective augmented, what it really means is this. I'm just rewriting the system equations in such a way that I just don't see the variables. For example, I have a tendency to put a vertical bar where the equal signs used to exist. This augmented matrix represents that system of equations. It allows me to just not write the variables over and over again. Now, if I had some tools in my back pocket that allowed me to massage this matrix in such a way that I can transform it into this one. In rewriting a system of equations, I misspoke. In rewriting this augmented matrix as a system of equations, I think the first row simply tells me that x is equal to pound symbol. Second row tells that y is equal to percent symbol. And now I've got my point of intersection, or shall I say, my solution to the algebraic system of linear equations. So everybody, I don't have a lot of tools in my back pocket to transform a matrix of this form into this form. There's only three tools. I refer to them as my three elementary operations. Let me clean this up a little bit. So before getting to solving such a system of equations, I need to take a break and talk about those elementary operations. So take a peek at this system of equations. Now, using that technique called the elimination method or the addition method back in ninth grade algebra, didn't you come in and just simply, can I take that back for a minute? I want to say something first. Look at the system, and let me write this way. My question is this. In interchanging those two equations, does that have any effect on what the solutions are? Or is this system going to have the same solution as this system? Because I think the answer is, heck yes, these two systems have the same solution. Just interchanging location equations doesn't affect the solutions whatsoever. So in massaging an augmented matrix, my first rule is this. I can interchange any two rows. So that's one of my elementary operations. Second, in solving the system, again, using our elimination or addition technique from ninth grade algebra, didn't we sometimes just come here and just say multiply both sides of the first equation by -2? So with that step, look what I just did. I merely replaced one equation with a multiple of itself. Or back in matrix form, that means I can replace any row with a multiple of itself. It's another bad eraser day. So one more time. So in solving the system, just like I did a moment ago, we could go ahead and take the first row, multiply both sides by -2. And I'll do that correctly. But with that elimination or addition technique, did we just also take an extra step of adding these two equations together? Now I can just divide both sides by -11. I have my y value. I can get the x value just by taking the -11, substituting for y. I misspoke. So y ends up being +1. We know how to find x. We just put +1 for y into either one of these equations, actually any of the equations. So everybody, look what I just did. In a sense, I sort of took one row, replaced it with the sum of itself and the multiple of another row to get an equation that doesn't change the solutions. So that's my third and last elementary operation. So we can replace any row with the sum of itself and a multiple of another row. So let's see if you and I can't use a series of these operations to actually solve such a system of equations. So here I go. I've already rewritten the first system of two equations, two unknowns, as an augmented matrix. And to reduce this matrix, here I go. I plant my feet in the first column. I look down and identify which entry in the first column resides on the main diagonal. And I'm going to force that to be 1. I will then force everything else in that first column to be a 0. So to take care of the red action, how about if we go ahead and replace the first row with 1/2 times itself? We'll take 1/2 times the first row and use our new first row. Next, I'll force this 5 to be a 0, but typically when I want to force them to be a 0, I simply use the most previous row for which I created a leading 1. And so that'll be the first row. Notice if I multiply the first row by -5, add it to the second, and use the results from the new second row, that'll force that entry where the 5 is to be a 0. Because I can do this. So how about my first row not officially changing yet? I only multiplied by -5 in my head. My second row is a 0. Oops, that's not a good 0. Now let's see. Is this -15 plus 12 is -3 And let's see, how about a -10 plus 7 is -3? I finished my task on the first column. Now it's time to move to the second column and force the entry that is in the second column that resides in the main diagonal to be a 1. And force everything else in that second column to be a 0. To take care of the red action, how about if we just take -2/3 and multiply to the second row and use the results in the new second row? So let's see, does that mean my first row doesn't change? And lastly, to force this entry right here to be a 0, let's just take -3/2 times the second row, add it to the first row, and use the results of the first row. Now, officially, again, my second row doesn't change. I'm merely going to multiply by -3/2 in my head, add it to the first. Is that going to be a -1? That being the case, I do think my solution, or my one solution, is the following. I'll use my set notation. Is the order pair -1, 2? Well, that was pretty quick. Well, actually, that was quick simply because it was a system of only 2 equations, 2 unknowns. For a system of 3 linear equations, 3 unknowns, let's apply it again. Now, keep in mind, this technique of Gauss-Jordan elimination only works with a system of linear equations. If the system isn't linear, as a mathematician, I don't have a single technique to solve such a system. For example, here's a system of 2 equations and 2 unknowns that are not linear equations. So here I go. I'm going to rewrite my system as a single augmented matrix. So is that 2, -1, 3, -1? 1, 1, -1, 6. 3, 2, 1, 9. Now I need my board space. I'm going to erase my system, but my system's singular. But let me just make sure I wrote down my numbers correct, my coefficients. And looks good. All right, I like it. So let's plant our feet on the first column. Force the entry in the first column that resides along the main diagonal to be a 1. When we're done, we'll force everything else in that first column to be a 0. Now, unlike my last example, maybe this time around, let me restate that. In my last example, I replaced the first row with multiple itself, and I can do that. We will clearly just multiply the first row by 1/2 to force that entry to be a 1. It just happens to introduce fractions early. So if you don't mind as an alternative, how about if we just merely take the first 2 rows and interchange them? So that gives us this. Next on my list, I'll force everything else in the first column that's not along the main diagonal to be a 0. So I'll use the most previous row for which I forced the leading one to exist. That's the first row. And I'm going to, if I multiply by -2, add it to the second row, use the result of my new second row, that'll force that 2 to be a 0. And I think likewise, -3 times the first row plus the third row. I'll use that as my new third row. So let's see, officially the first row does not change. Now my second row becomes a 0. Is that a -3? Is that a +1? Oh, excuse me, that's a +5. And lastly, is that a -12 minus 1 is -13? My new third row becomes a 0. Is that a -1? Is that a +4? And finally, I have a -9. Now I succeeded and completed my tasks on the first column. Let's move to the second column. And in the second column, I'll force this entry along the main diagonal to be a 1. And everything else we will force to be a 0. So take care of that red action. How about just taking a -1/3? Multiply the second row. Use the results to your second row. So let's see. Here's my first row unchanged. Here's my new second row. My third row at this stage doesn't change. Now, next on my list, if I come in and I force something of the form, hold that thought, let me just double check my arithmetic. So next on my list, everybody, I'm sorry, I'm stalling. I'm only stalling because I'm noticing if I take negative 1/3 times the second row and multiply the second row, I'm just creating more fractions. So just only because I can. Do you mind if I just come in and instead maybe multiply the third by -1 and interchange it with the second row? And that will allow me to avoid fractions. Not that I did anything wrong, I haven't. But again, avoiding fractions because I can. I'm going to take -1 times the third row and interchange that with the second row. So I'm being a little fancy. And look, it allows me to have another matrix. Same solutions, I just don't have fractions. Now let's see, next on my list. Let's finish up our business second column by forcing these two entries to be zeros. I can force that entry to be a 0 just by taking the second row, multiply by -1, add to the first row, and use the results to do first row. I can likewise say take negative or take +3 times the second row, add it to the third, and we'll use the results to do third row. So that being the case, is that going to generate the following? So my second row officially doesn't change yet. And let's see, my first row transforms to 1, 0. Is that going to be a -3? Oops, that's going to be a +3. So -1 times the first. What have I just done? I meant to say -1 times the second plus the first is going to give me 1, 0. And is that going to give me a +3? Is that going to be a -3? And alas, 3 times the second plus a third is very quickly giving me 0, 0, but now I got to slow down. So is that a -12 plus 5 is -7? And let's see. Is that an 18 minus 13? 18. I should say 27 minus 13 is 14. Gee, everybody, I'm starting so slow today. So I've taken care of business in the second column. Let's move to the third column. So yet again, we're going to identify which entry in the third column lies in the main diagonal. W minus -7, force to be a 1. And then force everything else in that third column to be a 0. Now, I do think I could force this entry to be a 0. Oops, I misspoke to 9. Let's take care of the red action first. Piece of cake. We're just going to take -1/7 times the third row and use the result of a new third row. So does that give us a first row that doesn't change at this stage? Same with the second. Does that give us this? And lastly, I can force these two entries to be zeros merely by taking, say, how about -3 times the third row? Adding to the first, that gives our new first. Or better yet, how about 4 times row 3? I shouldn't say that yet. In addition to 4 times row 3 plus row 2 will give us our new second row. Officially, our third row doesn't change. My new first row becomes 1, 0, 0. And let's say -3, is that going to be a +3? My second row becomes a 0, 1, 0 something. Let's talk about that something. Is that going to be -8 plus 9 is 1? Well, look at that. If I rewrite that back in equation form, let's see what it really says. It says we have a solution. which is a set containing a single order triplet, whose entries are 3, 1, -2. We've solved the system, the original system at the board, by using Gauss-Jordan elimination on an augmented matrix. Or I could have said we completely reduced our matrix so that we have ones down the main diagonal, zeros everywhere else to the left of that vertical bar, if possible. Sometimes it's not possible. Let's talk about that really quick. I'll be very brief. So take a peek at that very first, I take it back. Can we just take a peek at all three of these matrices? I'll transform this to one. I would say that all three of these examples are matrices in reduced form. Sometimes I say completely reduced form. The reason is for 4 reasons. So let me give you the 4 qualities of a matrix being completely reduced. Number 1, any row containing full zeros has to be at the bottom. Number 2, any non-zero 1 starts with a 1. I'll refer to that as my leading 1. Notice in this example, every non-zero row starts with a leading 1. All 3 are non-zero. Here, only 2 rows have non-zeros in them, but both those rows start with 1. Same applies to the third example. So my third quality of a completely reduced matrix is that every leading 1 you see has got to be to the right of any leading 1 above it. And I think all 3 of these examples satisfy that condition. Lastly, my matrix is completely reduced as long as every column containing a leading 1 contains zeros everywhere else. And again, all 3 of these matrices solve that 4th quality. So I do think all 3 of these matrices represent system equations where the matrix itself is completely reduced. Now let's talk about how we can write our solutions in these particular cases, unlike the case I had with the example on the back of that I just erased. So look at the 3rd row of the first matrix. Rewriting this back in equation form, doesn't that say 0 times x plus 0 times y plus 0 times z equals 1? Or better yet, 0 is equal to 1. Well, that's a contradiction. 0 is not equal to 1, so it kind of suggests that the original system equation this augmented matrix represents has no solution. And I don't know how you want to write that. You can say it in words. Some people just use set notation with nothing in it. Personally, I like to use this notation because that represents the null set or the empty set, the set that contains nothing. But all 3 of them mean the same thing. Now let's take a peek at what this augmented matrix is saying. Hopefully you agree I satisfy those 4 qualities to be completely reduced. But now rewriting that augmented matrix back into equation form, here's what the first row says. Here's what the second row says. Those 2 equations share a common variable z. I'm going to give z another name. I'm going to go ahead and let z be equal to, say, I typically choose t as my parameter, only because of a lot of applications that represents time. So if I let z equal t, notice what the second equation says. The second equation says that y is equal to 1 minus 3t. Now take a peek what the first equation says. It says that x is equal to -3. minus 2t. But my solution should be an order triplet. So here's how I'm going to write my solution. I'll use what I refer to as my set building notation. So I got an order triplet where x is negative 3 minus 2t. Y can be expressed as 1 minus 3t. Z can be replaced with just t, such that t ranges over the rails. That vertical bar simply represents the phrase such that when I use a set builder notation. And I'm kind of hoping my notation doesn't change relative to what you used back in 9th grade algebra. Now, I only have one parameter, so for me, that means the corresponding solution set contains order pairs on a line of intersection among the three original planes whose system was rewritten as an augmented matrix, which was transformed into this completely reduced matrix. Let me finish up by talking about that last example. If a system of three linear equations, three unknowns, has an augmented matrix that reduces to something in this form where two of these rows are full of zeros, it just simply means the points of intersection correspond to a plane. What plane is it? Well, it's actually the plane described by any one of those three equations. However, if I rewrite this back in equation form, doesn't it say this? And if we let y be equal to s, and let z be equal to t, then corresponding, I do think it forces x to be a negative 2s. Is that a plus 3t plus 4? And so I probably write my solutions back in solution set notation form as such. So x is negative 2s plus 3t plus 4. Y is s and z is t, such that both s and t range over the rails.